very much. Thank the organizers for the invitation and the opportunity to talk here. And since I'm the last speaker, I should also thank the organizers on behalf of everyone here for a wonderful conference and a wonderful week. Okay. So I'll be talking about projective structures. This is a joint work with Shinpei Baba from a couple of years ago. So yes, X, in case you were wondering, throughout the talk is going to be a closed and oriented surface of genus bigger than or equal to 2. So let me give a couple of descriptions of what a complex projective structure is. So start with a sort of a local description. So it's a local system. It's a geometric structure modeled on the Riemann sphere, CP1. So you have charts to CP1. So here's the surface, such that the transition maps, defined on the overlaps, are in restrictions of automorphisms of CP1. So these, on the overlaps, they are Mobius transformations. So that's one description of a complex projective structure. And I'll be looking at sort of marked complex projective structures. By marking, I mean a choice of a homeomorphism and identification with this fixed topological surface S. So C here will be a projective surface. So this is a marking. Notice that this such a structure also defines a complex structure. So it's also, there's an underlying Riemann surface. So that's a local description, and a more global definition is in terms of the developing map and the holonomy. So there's a developing map from the universal cover of the surface to CP1, which we obtain by this global map, which you obtain by piecing together these local charts to CP1. And one can do it on the universal cover. One can't quite do it on the surface because for a loop coming back, there might be a mismatch. The charts might differ by a automorphism. And so that mismatch is precisely, it gives this holonomy representation, the monodromy of this geometric structure. This is homomorphism to PSL2C, which is the group of these Mobius transformations. Okay, and so this developing map is equivariant with respect to this rho. So it takes this action by deck translations on the left to some action by Mobius transformation, some gamma, where gamma is going to denote the image of this of the fundamental group under this representation. Okay, so this pair of F and rho determines a marked complex projective structure, and conversely, so there's given this local description, you can, as I described, figure this out. There's some ambiguity of this choice of a developing map. It's defined only up to a post-composition with an automorphism of P1, which conjugates the representation. So this is really an equivalence class under that conjugation. But this is an equivalent description of a marked complex projective structure. So I should mention that there are other sort of descriptions. So there's the things involving bundles. So for example, this representation defines a flat CP1 bundle over the surface, and the developing map will be a section of that bundle which is transverse to the fibers. But I won't go into that. And so the other descriptions like that, there are SL2 opers and so on, so which are maybe of interest to the Higgs bundles community. So for me, it will be these descriptions. And more generally, I should point out that you have what are called GX structures on manifolds. On a manifold M, and this is a special case of that here. G is some Lie group, and X is some space on which this Lie group acts, like a homogeneous space. So these are rose earlier in this conference, and so the objective is to kind of understand the deformation spaces of such GX structures and manifolds, and this is a special case. Okay, so again, let me give a couple of examples of complex projective structures, so which are well known, you're familiar with. So the first one is our Fuchsian structures. So this is the case when the group gamma is actually a discrete subgroup of PSL2R, which is inside PSL2C. So in this case, the gamma action on CP1, it preserves the real line, the equator, and the upper hemisphere, which you can identify with the hyperbolic plane. So this is the image of the developing map, and that's nicely, it's a discrete group, and this quotient gives you this Riemann surface with this Fuchsian projective structure. And as you know, any Riemann surface can be uniformized to such a structure. So these give you some examples. There are other examples. So on a Riemann surface, you can also have another classical example of Schottky uniformization. So here, this gamma would be a free subgroup of PSL2C generated by G loxodromic elements. So these act on CP1 by preserving, so taking these G pairs of circles, and they take one to the other. And once again, so this gamma action on CP1, so there's some nice domain on which it acts. It's the complement, some Cantor set, and the quotient gives you this Riemann surface. So these are examples of complex projective structures, but later we'll see that given a Riemann surface, there in fact is an entire vector space, 3G minus 3-dimensional vector space worth of such structures, and those need not be so nice that the developing map could in fact so not embed like this, but it could wrap around the sphere several times, and the representation could be an indiscrete representation, unlike these discrete ones here. So we'll see more examples later. So sort of the what we shall study this talk is going to be the holonomy map. So the objective is to try to understand what representations arise on which Riemann surfaces. So P of S would be space of marked CP1 structures on S. And so we can define the holonomy map to the character, PSL2C character variety. So these are homomorphisms from pi1 of S to PSL2C after conjugation. So this is just by forgetting about the developing map and recording the holonomy, the monodromy of the geometric structure. And on the other hand, we can also forget complex projective structure and just look at the underlying Riemann surface. And this gives you a projection to Teichmuller space, the space of marked Riemann surfaces. And of course, there's a further projection down to moduli space, the Riemann moduli space, where quotient by action of the mapping class group that acts by changing markings. So the theorem that to talk about today is this joint work with Baba, and it's about the fibers of this map. So it's as follows. So if you let rho, some representation belong to the image of this holonomy map, and I'll later describe what exactly this image is. So almost every representation is in the image. So then this holonomy fiber, so the inverse image rho, it's some set in the space P of S, it projects to a dense set in moduli space. Okay, so in other words, if you look at complex projective structures with the same fixed monodromy, the underlying conformal structures, they're dense in moduli space. And so I'll talk about this, the idea of the proof at the end. So sort of the plan of the talk is I'll first say a bit more about this these spaces here and this picture here, more about the holonomy map and about this space P of S. And we can parameterize it in different ways. There are classical parameterizations using the Schwarzian derivative. And then I'll talk about a more geometric parameterization by what I call grafting deformation. So the grafting parameterization of P of S. So this is due to Thurston, and then I'll talk about ideas of the proof of this theorem. So, so I'd like to kind of sort of emphasize this parameterization, as we shall see, as sort of, kind of a geometric way to understand complex projective structures, and it might be interesting to sort of see whether there are other such geometric structures of higher rank, like the PSL-NC, which also can be sort of, so it also has some corresponding such parameterizations and sort of ways to deform structures. So this projection is going to be surjective, as we shall have already seen. Yes, I'll mention that later. Yes, yeah, it's going to be discrete. Yes. This will be 6G minus 6, and I'll say complex dimension. Yeah, so I'll mention, I'll say more about this. But let me start with some kind of a toy example. Which it's nothing to do with the proof, but it's an illustration of this result in the case of genus equals 1. Okay, so which is not, I didn't state my theorem for that, but it also holds, and our techniques would extend to sort of prove this in this case. So here you have the torus. The Teichmuller space of a torus is the upper half plane, and if you pick a conformal parameter here, the tau, so the universal cover is the complex plane, and it's quotiented by these two translations. Z goes to Z plus 1 and Z plus tau. So that's the universal cover, and to specify a complex projective structure, I'll need to tell you a developing map and the holonomy. So the developing map that we can take in this case is the exponential map. So C is some non-zero complex number, and we can check that this case the representation. So then in fact this will be an affine structure, and there's some sort of the abelian sort of group here, and so here gamma so generated by these two homotheties, these dilations at fixed 0 and infinity, we can check that this F is equivariant with respect to this rho. So that's an example of a complex projective structure on the torus. And if you fix this representation, if you want to fix this representation and choose some other structures, so there were some choices involved here. You can choose your tau, this conformal parameter, and then also this complex number C. So you want to choose C prime and tau prime to get the same representation, and it's very easy to see here that you get, well, you just need to have these e to the C's, e to the C taus match up. So you have some kind of infinite set of solutions. M and N are integers. And you can plot these parameters in the Teichmuller space of the upper half plane, the Teichmuller space of the torus, and you'll get some kind of discrete set. And our theorem says that if you project them down to SL, this moduli space here, so it's going to give you something that's dense. So, so there might be a more elementary way of seeing this in this particular case, which, but I don't know. But our more general techniques that we'll mention later also covers this case. So, so let me start with a bit more about these spaces here and the holonomy map. So as I mentioned, if you fix a point in diagonal space, and you look at all complex projective structures with that same underlying Riemann surface, that turns out to be equal to, or can be identified with the space of holomorphic quadratic differentials on X. So, and this is 3G minus 3 complex dimensional. So let me give some idea of how this works. So if you fix a uniformization, a Fuchsian structure on X, so you identify the universal cover with H2. So then the developing map F becomes some meromorphic function, and you can look at its Schwarzian derivative. And the Schwarzian derivative of the developing map then gives you a quadratic differential. Okay, so I won't say what Schwarzian derivative is, but it's a differential operator that exactly sort of measures the deviation from being Mobius locally. So now, so that's sort of one way, and the other way you have to sort of solve this equation. If you fix a quadratic differential, you want to find a developing map, and then so this also determines the monodromy. So this for this you need to kind of solve a particular second-order linear differential equation of the Schwarzian, and then sort of the two solutions of this, so that the linearly independent, the ratio gives you this developing map. So that's an idea of how this is identified with the space of holomorphic differential. So there are plenty of structures. Even if you fix a conformal structure, an underlying Riemann surface, and this gives you more examples. So I mentioned this Fuchsian and Schottky examples before, but for any quadratic differential, you will have some complex projective structure. So in particular, if Q is small, so I should say that if this quadratic differential is 0, then you recover this Fuchsian uniformization that you picked. But if Q is small, you get something called quasi-Fuchsian structures. So in this case, the developing map will be some kind of quasi-disk. It won't be the upper hemisphere, but it will be some domain. The developing map will still inject, just like in the Fuchsian case, and there will be this domain bounded by this. This will be the image of the developing map, and the quotient, the group will still act nicely. It will still be a discrete representation, and the quotient will give you this Riemann surface X. So there are many such structures, and this again the developing map embeds, but if Q becomes large, all sorts of wild behavior happens. Your developing map might overlap and so on. It's an immersion. So there are more such structures, and so this entire space P of S can be then thought of as this is an affine bundle. So we had to fix this section, this Fuchsian uniformization, and then so the differences of projective structures are measured by these holomorphic quadratic differentials. So it's an affine bundle modeled on the vector space of quadratic differentials in diagonal space. So it's a 6G minus 6 complex dimensional space. And let me say a bit more about what the holonomy map does to these fibers, these inverse images. So there's a fact the fact that the holonomy map, when you restrict it to this pre-image, so here's a picture. So P of S is one of these fibers, the inverse image of a point, Teichmüller space. So if you under the holonomy map, this gives you a half-dimensional complex submanifold here in character variety. So, so this image is a proper embedding. So this fact goes back to Poincaré, the classical result. But there's more is true if you take a compact set in Teichmüller space, and you look at the pre-image of that. So here's the compact set, pre-image of compact set in space of projective structures. Then also this the holonomy map is a proper map to its image. So so maybe it now is no longer embedding; it overlaps, but the map is proper. So this is due to Tanigawa. So these are what happens to these if you fix the conformal structure, but we are interested in varying X over Teichmüller space. So let me say more about this holonomy map, which is now in that board. So it's known, so the image of the holonomy map is known. So in the image of Hall equals all non-elementary representations that lift to SL2C. So it turns out that this character variety has two components. One's representations that lift to SL2C and the component representations that don't. And so these non-elementary representations are almost generic in, so almost every representation in that one component are non-elementary. And one thing you can think of if you don't know what it means is it's kind of irreducible and it's not unitary. So anything not unitary and irreducible is sort of is achieved as the holonomy or the monodromy of some complex projective structure. So they are quite generic in the character variety. So this is a result of Gallo, Kapovich, and Marden. So it's also known that this holonomy map is a local homeomorphism due to Hegel. So this is a more general fact about GX structures on manifolds and the deformation spaces. If you look at the monodromy of such structures, defines a local homeomorphism, sometimes called the Eresmann-Thurston principle. But in this case, sort of Hegel sort of studied this Schwarzian equation and proved this fact. And he also showed that it's although it's a local homeomorphism, it's much more complicated than just a covering. So it's but is not a covering map. So in fact, it is a covering when you restrict to quasi-Fuchsian characters. So representations like these are some kind of open set. They form some kind of open set in the character variety. By the way, so these are all non-compact, but this is for the cartoon. I'm drawing it this way. So now the holonomy map, if you restrict to the quasi-Fuchsian characters, it's a covering. So there are these exotic quasi-Fuchsian structures, but these accumulate on each other. So it's not a covering if you were to go beyond this. Okay, so the holonomy map, very interesting, complicated map, and the other thing that was known was that the holonomy fibers, as I mentioned, the inverse images of a particular representation in the image, are infinite. Okay. So this we'll see later how this comes about. This is implicit in the work of Gallo, Kapovich, and Marden, but this was greatly clarified by recent work of Shinpei. So. And we'll see this later. And in fact, so we now prove that they are also, if you project down to moduli space, they are dense. So let me now introduce this grafting parametrization. It's the main tool. So grafting is a way of deforming a complex projective structure. So we start with a Fuchsian structure. So here the developing image is this upper hemisphere, H2. There's this subgroup of PSL2R that acts here, and its quotient is this hyperbolic surface. I didn't mention it, but now, so around this carries the Poincare metric, so you also have this hyperbolic metric here. So you choose a gamma, a weighted, simple closed geodesic. So that's called the weight W. So this is some kind of curve like this, where weight some real number. So its image under the developing map gives you this equivariant collection of these lines in the upper hemisphere. So this is a Fuchsian structure, and let me describe a way of deforming it to get a new complex projective structure. So this is this process of grafting. So what one does is one sort of bends this image of this developing map. So the best way to think of it is think of the interior of this ball as being the copy of hyperbolic 3 space, and the boundary at infinity is CP1. So then this equatorial plane embeds as a totally geodesic copy of the hyperbolic plane. And over here, you also have these lifts of these geodesics. So these are related to the boundary at infinity by a hyperbolic Gauss map. And now, so you can, what one can do is one can bend this plane. So at every copy of this geodesic, one rotates one half of the figure by an angle which depends on this weight, W. So at infinity, on CP1, so this half of the developing map now rotates relative to the other, and there is this some angle, and there is some crescent-shaped this region that you've introduced, you've grafted in, and this is you do equivariantly. So what I've described to you is this new developing image, the image of the developing map. And the group, since you're sort of rotating, these are elliptic elements of PSL2C, you have a new Mobius group that acts on this figure. And so you get a new projective structure. So this new gamma prime is now another subgroup of PSL2C. One way of seeing what it is so on this subsurface, you are fixing the representation of this. So suppose the curve separates, you're fixing the representation on this subsurface and conjugating the restriction of the representation on the other subsurface by this elliptic isometry, this elliptic element. So you have this new Mobius group and a new projective surface, and so this quotient you can visualize as you've added in an annulus. So this annulus is the quotient of this crescent-shaped region. So remember that this group, the element corresponding to gamma, acts by translations along this geodesic, and here this gives you this projective annulus in the quotient. So this surface I will denote by the one obtained by grafting X along this omega, this W times gamma, this weighted simple closed curve. So that's one way of deforming, but this can be, so now you can do more, you can graft along limits of such simple closed curves. So this is sort of one innovation of Thurston. So you can graft along what are called measured laminations. So what is a measured lamination? So it's So here's, once again, you have a hyperbolic surface. A measured lamination is going to be a foliation by geodesics. So it's a closed set in X that is foliated by simple, which means non-intersecting and complete geodesics. So one example is, of course, just a single simple closed curve. That's a lamination. But more generally, you can have uncountably many leaves spiraling across the surface with some kind of Cantor set cross section. So it can be a very complicated object. This is just a cartoon, and it carries a measure. So there's a transverse measure with the foliation. So for the case of this weighted simple closed curve, this weight can be thought of as a Dirac measure on the curve. And so here there is a so for every transverse arc transverse to this foliation, you can attach a positive number that sort of measures how much the leaves passing through the foliation are worth. And this is invariant when you slide this arc along the leaves. So it's invariant on the holonomy of the lamination. So these objects, all these measured laminations, in fact, form the space ML and some finite dimensional space. So these objects you can think of as you can combinatorially represent them as what are called train track graphs. So these are so if you stand back and bunch together these leaves, these give you some graphs on the surface with some weights. And these weights satisfy some kind of additive relation at every vertex. So these are called weighted train tracks. And these combinatorial objects, they parameterize all such measured foliations, measured laminations. All right, so once you have such a geodesic lamination, you can lift it to the universal cover, and you have some kind of, so these geodesics lift, you have some kind of pattern that actually there's some kind of tree-like pattern that I won't try to draw, that's sort of, it's modeled on the lift of this train track graph. And this is now the copy, the universal cover that you embed as the equatorial plane and use these transverse measures to bend. Okay, so this process can still be defined for a measured lamination, and so so you can define the resulting grafted surface. So a new complex projective structure you get by bending along the lamination. And the theorem here, which is what we'll use to Thurston, is that this grafting map from Teichmüller space cross ML, so you can choose your Fuchsian structure and your measured lamination and then bend to projective structures, is a homeomorphism. So in fact, so this parameterizes the space of projective structures. So in fact, there is an inverse that one can construct. So given a projective structure, how do you recover this grafting that you need to do? So you look at the developing image, and the developing image, you look at the maximum round disks that you can embed, and look at the convex hulls of those. And the envelope of these convex hulls will give you this bent surface, which is the pleated plane. It's called the pleated plane. And this, from this description, you sort of recover the Fuchsian structure and the lamination you need to graft to get to that complex projective structure. So that's a rough idea of how the inverse works. All right, so let me mention two consequences of this parametrization that are things we are going to use. So one is from this description, we can extract a notion of 2 pi grafting. So observe that if you start with a Fuchsian structure, X, like here, and then you bend, so you take a weighted simple closed curve, but with weight W, which is 2 pi. So then, as I mentioned, you bend by an angle determined by the weight. So if it's 2 pi, you bend all the way, and you conjugate the representation to itself. So the resulting, this operation doesn't change the Fuchsian holonomy. But it does give you a new complex projective structure because now the developing map wraps around the sphere once. So if you have a Fuchsian structure, so the observation is that grafting along 2 pi times some simple closed geodesic preserves the Fuchsian holonomy. So one way of visualizing what this does is, so let me describe what happens to the developing map. So the developing map now, so here are the lifts of gamma tilde. So at every lift, so you now wrap around this CP1 once more. So you take a copy of CP1 with a copy of this lift, this arc, and it is this picture that you slit and splice in. So this, and you do equivariantly, and this gives you the description of the new developing image. So it sort of wraps around CP1 several times. Okay, so this you can do. Now this was for a Fuchsian structure, but you want to do it for some arbitrary complex projective structure. So this process you can do as long as this lift of gamma, this developing image of this lift of gamma embeds. So suppose you have some kind of embedded developing image. So once again, you can take a copy of CP1 with this arc, this identical arc deleted, and you can do this splicing in, and this will define a new developing map with the same holonomy. So these arcs, let me give a definition. So an admissible loop on gamma on C is one such that, so firstly the image of the developing map embeds in CP1. It doesn't intersect itself, and for technical reasons we also need a row of gamma is loxodromic, has 2 fixed points, and so this got 2 distinct fixed points. So this observation leads you to the more general fact that so if you sort of do this 2 pi grafting, grafting with weight 2 pi along an admissible loop gamma on C, you don't change the holonomy. So you preserves the holonomy of the projective structure. It changes the conformal structure, as we shall see. So this grafting along a loop, you introduce this cylinder, so you change the modulus of this curve, but you preserve the holonomy. So this is nice, but the trouble is that it might be difficult to find admissible loops because, as I mentioned, that a complex projective structure developing map could be pretty wild to CP1, and it could and then so find a loop whose developing map, developing image embeds might be hard. But there's this fact, the theorem of Baba from earlier, which says that if you look at projective structure by Thurston's theorem, we know that it's obtained by grafting X along some lamination L. So then any loop gamma that intersects L at a small angle, so I'll not be very precise, a sufficiently small angle is admissible on C. So the idea of this is, so suppose you start with this, so the equatorial plane, which is our x, and you have this lamination L. Then initially, this loop gamma is something that is going to intersect L at a very small angle. It's going to be almost parallel to L. So initially, this developing image will embed as any, it's in the Fuchsian structure. But so typically when you bend, this developing image will sort of intersect itself. But if the intersection angle with this bending lamination is very small, then as you bend, so when you bend the amount it moves is small compared to the distance along this direction. So the developing image still embeds. So that's the idea behind this this theorem, and once you have an admissible loop, you can do this 2-pi grafting, and so a corollary of this is something I mentioned before, that these holonomy fibers are infinite, because you can do this 2-pi grafting, this kind of bubbling process, as many times as you want, some 2-pi n grafting, and so all of these are going to have the same holonomy. So this is how you prove that these holonomy fibers are infinite. So this is one consequence of this Thurston parametrization. And let me mention one more ingredient that one can extract from this. So this is called conformal grafting. So this time we look at the other projections. So you have projective structures and you look at the underlying conformal structures. So now when you graft a Fuchsian structure along the lamination, you can also look at what happens to the underlying conformal structures. So, which I'll denote by little gr Lx. So as an example, as I mentioned, if you look at sort of a simple closed curve, then the grafted surface, you are sort of, changing the modulus of this curve because you're introducing a cylinder. So in Teichmuller space, you move when you do this grafting, and in fact, you get a parametrization of Teichmuller space. So the theorem of Dumas and Wolff is that if you fix this some base point, some x in Teichmuller space, and you look at the grafting map, and you vary the lamination, then you in fact parameterize Teichmuller space. So this grafting, a conformal grafting map is a homeomorphism. So in Teichmuller space, this gives you some kind of polar coordinates. So ML is not quite a vector space, but it has a ray structure, because you can scale the measures on a measured lamination. So for every lamination L, you can look at what is called a grafting ray, which is obtained by scaling the measures, of bending more and more. So this gives you some, so this ray in Teichmuller space, so this theorem says that this is in fact some kind of polar coordinates for Teichmuller space. The theorem of mine is that if you sort of project down to these rays to moduli space, so these get dense. So for any x Teichmuller space, and almost every lamination in ML, you have the grafting ray based at x, and graft along L, it projects to a dense set in moduli space. So I won't talk about the proof of this, but let me just mention that it's a consequence of the fact. So you can compare this picture, these polar coordinates, with the Teichmuller exponential map. So it's a consequence of a certain asymptoticity in a strong sense of these grafting parametrization with the Teichmuller geodesic rays. So these grafting rays with Teichmuller geodesic rays. All right. So yes. Sorry. Yes, your Teichmuller geodesic rays with respect to the Teichmuller metric, which is the Kobayashi metric on Teichmuller space. Yeah. So these grafting rays, in fact, are dense. So the idea of the proof of this, the theorem I mentioned at the beginning, so idea of the proof of the holonomy fiber projection being dense. So I've erased the theorem. So this was the theorem. Is as follows. So if you, it can be expressed simply. So if C, let's say, is a projective surface, is a surface with a projective structure with holonomy rho. So what you have to do is you approximate a dense grafting ray. So something that's dense in moduli space with 2 pi graftings of along admissible loops on C. So this is the sort of the general idea. Let me give a few more details. So if you have so the C can be thought of as so by the Thurston parametrization you obtain it by grafting so some Fuchsian structure by along a lamination. So now so this has holonomy rho. So suppose for simplicity that this if you continue grafting, this conformal grafting ray along X is dense in moduli space. So then we have this picture. So you start with this Fuchsian structure and this lamination L, and then you graft along L and you get to C. So grafting along a lamination, just like a simple closed curve, you add an annulus here. Well, there are not many geodesics typically, but you can think of it sort of fattening this lamination. So that's our C. So suppose that this continues to give you a family of these one-parameter family of these projective surfaces whose underlying conformal structures are dense. So this sort of exists by this theorem. So then what you want to do, so the more precise version of this general idea is you want to approximate this with 2 pi n graftings. So in other words, for any epsilon and all sufficiently large T, there exists some admissible loop n on this projective surface such that these grafted surfaces are epsilon close in Teichmuller space. So since this is getting dense in moduli space, getting close to any Riemann surface, so by this proposition, so would this. Okay, so that's the more precise version of this idea. So let me give some idea of how this works. So there's two things I need to maybe say. That how do you pick this admissible loop n? And then to show that they're epsilon closed, we need to build a 1 plus epsilon quasi-conformal map. This is the notion of distance, the Teichmuller metric and Teichmuller space. It gives the topology in Teichmuller space. So I don't have time to say much, but let me. The two things are to choose an admissible loop, and you build this F. So this N, let me just say that it is obtained by some kind of integer approximation of the train track corresponding to this lamination. And you have to pick it very close to this line, intersecting at very small angles so that it's admissible. Okay, so that's a rough idea of how N is chosen. But to build F, so we show that we have to build this map, and it's going to be an isometry outside some kind of neighborhood of the lamination, and everywhere else it's 1 plus epsilon bilaterates with respect to some conformal metric that we build on to surfaces. So let me just say where the idea of this comes from. So this is something that appears before, but we had to modify. Well, we have to do it differently. So the inspiration for this conformal metric, so there's a more general the projective metric you can define on a complex surface with complex projective structure. This is due to Thurston in this case we have been talking about, and more generally for higher dimensional Mobius manifolds, the conformally flat manifolds due to Kulkarni and Finkel. And this projective metric is defined as follows. So recall that on a complex manifold you have a Kobayashi metric, pseudometric, which is defined by, if you take a point, here's the Riemann surface, the general complex manifold, a point in the tangent space, then the norm, the Kobayashi norm of this vector is defined to be, you look at all maps of the disk with the Poincare metric to X. So these are holomorphic immersions. And you infimize the sort of the pulled back norm of this vector with respect to the Poincare metric. So now for a projective structure, so you can have the same definition, but so the projective metric, you look at projective immersions, sort of bounded below by the Kobayashi metric. And this defines this metric. So let me give some idea of what it looks like. So in other words, in our complex projective surfaces, you have this developing map. So at every point, you can look at the largest maximum round disk that you can embed. That's a projective immersion, and the Poincare metric at the center of it. And this defines the metric. So on the upper half plane, so let's say you look at a Fuchsian structure, this recovers the hyperbolic metric. The largest disk is the upper half plane itself. So that's the hyperbolic metric. But when you do this grafting, you bend it. So this is another picture of this bending. So you can remember you add this disk, this region, this crescent-shaped region. So then this projective metric on these parts remain hyperbolic. But points in this grafted region, the maximum disk is given by this distance to the boundary. So here, the metric looks something like this. It's a Euclidean metric. So on the grafted surface, what you see, the projective metric, if let's say you do grafting along an annulus, along a simple closed curve, on this annulus you have a Euclidean metric, and on the complement you have hyperbolic metrics. So it's going to be something which is sort of a C1 metric, not a C2. This curvature is discontinuous here. But this is something that's conformal with respect to this original Riemann surface structure, as we see, and And so we can you can sort of build bi-Lipschitz maps with respect to some such structure. So if it's a more complicated lamination instead of a simple closed curve, then this metric is more complicated. So we don't use this, but some sort of adaptation of this to build our metric, and we build our maps this way. So that's all I'm going to say about the proofs. Let me end with some sort of further question and the context in which this we started looking at this. So, so the context is if you have this, the action of the mapping class group on the character variety. So, so remember that we have the holonomy map from these are complex projective structures of the character variety. This is equivariant with respect to the action of the mapping class group that acts by changing the markings on the left, and it acts by precomposing the representation with the induced map on the fundamental group on the right. This is a basic question of what the geometric structures look like up to this this action up to change of marking, and the conjecture of Goldman is that in the PSL2C character variety, so the action of this action, the mapping class group, is ergodic outside the quasi-Fuchsian characters. Okay, so remember we had this cartoon. You have the quasi-Fuchsian characters. The representations sit as an open set inside the PSL2C character variety. Here, the action of the mapping class group is nice, but the conjecture is that outside it's chaotic. So the idea was to sort of try to probe that action using this equivariant map, because some of this separates points as the holonomy fibers are infinite, and in fact, this conjecture sort of implies our theorem for almost every representation outside quasi-Fuchsian characters, or this space of quasi-Fuchsian characters. But this is not really any positive or negative sort of indication towards the conjecture. But nevertheless, the idea was that this might be useful. So, so this is the context, and let me sort of end with a couple of other further questions. So one is that we saw that if you take the pre-image of a point, it projects to a dense set. So does if you take a pre-image of a small ball, so B rho is a so let's say radius epsilon ball in character variety around this representation. So does this project to the entire moduli space for any rho? So the answer is yes, this would be kind of interesting, because it means that for any fixed Riemann surface, you can choose a marking and a quadratic differential to approximate any given representation. And so this is something, a stronger version of what we showed that I don't know the answer to. And the other question, of course, is what I mentioned, the other sort of analogs of these results or these constructions, like the grafting one, of these in sort of in groups of higher rank, like BSL NC, which I don't know anything about, but maybe some of you can. Do I expect? I don't know. Yeah, so it's a question. Maybe not. So we already know it's dense. Right, the maps are, holomorphic even, so, the holomorphic projection. holonomy map is a locally biholomorphic. All right, so I think I'll end here. Right, so I should mention that this bending parametrization, thanks for the question, this bending parametrization of projective structures is an analog of that for the Hitchin component. You have some work by Bonahon and Dreyer, where again you have laminations, but this time instead of weights being real numbers, you have flags, and you can parameterize so these components of SLNR representations using well, the analog of bending in the real case. So there's something for these real representations, but I don't know that holds for complex PSLNC, and there's something like that. Yes, Riemann and Wolf, yeah. For minimal. No, I don't know what the relation is with minimal surfaces. Yeah. I know. Well, yeah. There might be something, but I don't know. I mean, I don't think anybody knows the relation. Yeah. Yes. No, I think it's kind of almost wide open. I mean, nobody knows. I mean, there are no orbits, no good examples of orbits which are dense, for example. So this would imply that almost every orbit, just quasi-frequency would be dense, but that's not known. And yeah, I don't know what the latest is. Right, so people have studied the action on the boundary of quasi-Fuchsian characters, but not.